Hey guys, we're going to walk through, this is problem 1 from your homework worksheet on adding and subtracting vectors. We'll walk through this one together, and that will hopefully give you a good enough piece of practice so that you can feel comfortable and confident trying the other 4 practice problems, and then we can continue to actually use this skill in some physics applications. So here we go. We're adding vectors, a plus b. I've drawn the 2 vectors as they appear on your worksheet, but not exactly in the same locations. I put some markings to help me out. I'll do my best to sort of talk through it without the use of the grid lines. So let's get started. So the statement of a plus b is the addition of 2 vectors, a and b. That's different than adding together 2 standard numbers. So this would not be the same as adding together 4 plus whatever the magnitude of b is and getting a number. We have to add them vectorially. The way we do that is using 2 techniques. One is the pictorial representation, or the diagram representation, tip to tail, and that will give us an idea of what the resultant or final vector looks like. And then what we can do is use components to help us get to what the actual solution is. So let's start into it. I've drawn the 2 vectors. A has a magnitude of 4 going down. So we'd say this in this diagram 270 degrees. So 4 at 270 degrees would be the vector and its direction. So what I'm going to do is redraw this in a little bit smaller scale down here. So there's my vector A going straight down, and I'm going to take b, and again, as long as I keep it in the same magnitude and same direction, the vector doesn't change. I'm going to take b and I'm going to redraw b right beside a so that it looks like this. But starting at the tip of a, we'll start the tail of b and go up like this. So here's b. So when you do that, one of the things you can see is that adding these 2 vectors together gives you the value that connects between here and here, because adding these together would actually give you your displacement if this was a position scenario where somebody was changing their position. And so as we go through this, we can see that got a different color marker here that might help. What I get is a horizontal line here. I'm going to call it vector r to stand for the resultant vector. So that represents our resultant vector. Now, how is it that we can figure out that value in sort of the most exact way? So in both knowing its direction and its magnitude. Well, the first thing you need to do is break down component vectors. So you look at your original vectors and you can see that a is already a component vector. It's a sub y actually vector, because there's no x component here. So this would actually be the same thing as saying a sub y equals 4, and then this would also mean that a sub x equals 0. If I come over to b and label its different vectors, I can see that b sub y would equal 4, and then I would see that b sub x would equal 5. I should also be clear here, because we're talking about the component vectors, that a sub y is negative because it has a direction associated with it. Now, if we want to figure out what the magnitude of this vector is, what I can do is actually add these values together simply by adding the ones that appear in the same direction. So I'm going to do this in 2 different ways. One is just mathematically with an equation. The other is using my pictures to help me out. So watch what happens here. If I take b and I break b up into its 2 components, watch what happens. B has an x component that we said was 5 right here, and b has a y component which we said was 4 right here. What those 2 vectors represent, 5 and 4, those 2 vectors represent the vectors that if you added them together, you would get back b. So they're equivalent. 5 plus 4 here will equal b. Because that's the case, what I'm going to do is I'm going to sort of scratch out part of b so we don't think of it still a vector that's there. And instead, we're replacing b with 5 and 4. So now I'm adding together a plus b, which is actually a plus 5 plus 4, considering their directions. Now remember, a is equal to ay up here, which is just negative 4. So because a here and this vector here are in the same direction, you can just add them numerically. And when you add negative 4 plus 4, what you get is 0. This makes sense from the walking example that we did. If you walked negative 4 and then you walked positive 4, you'd be back in the same spot. And so your displacement would be 0. So essentially we could say that this vector and this vector cancel each other out. In other words, add up to 0. That means the only vector that's left is this bottom vector in our picture, and that means that our bottom vector here has to be equal to our vector r. So we can actually say that vector r is equal to 5, but because it's a vector, we got to tell what direction, at 0 degrees, or I could also say 5 at, well, not 5 at, but we'll say 5 in x, and if this is positive 5 in x, will tell us that it's in the x direction. Let's do this numerically though. If I said add those two vectors together, here's how we could do that. I would take vector a plus vector b gives us r. So breaking this down, that means that a sub x plus b sub x, the x component of a, the x component of b, added together will give us the x component of r, and likewise the y component of a, the y component of b added together will give us the y component of r. So we can plug in numbers here because we already figured out what the components are to solve for this. So ax we figured out was 0, bx is 5. So that means that Rx is 5, and then AY is, let's see, AY is negative 4, plus BY is positive 4, which is 0. So what I found was that R sub x equals 0, R sub y equals 5. And so these two are your final vectors, components of the vector, r, and you can see that that matches what our picture says. R sub x equals 0. That means there's no x component. Sorry, something's backwards here. What did we do backwards? Oh, I just flipped them. R sub x is 5, because there's a 5 component there, and then this is 0, which means that the value is the same as what we wrote right there. So that is how you add together vectors. A quick word of caution on the next couple that you do before I let you go. The addition of two vectors a plus b is done like we showed here. But if I subtract the two vectors, you can essentially take that negative sign that's between the two. Let's say it was a minus b, and you can apply that negative sign to this vector, which would flip its direction. And by flipping its direction, what that would do is cause the signs of the two components to switch, and that would just impact and follow through the rest of your math. So if there's a negative sign, it's really just adding with a negative, and so you can just flip that value and you'll still be able to get to the solution thinking about it in terms of adding vectors. We've only looked at this though from the abstract sort of place of abstract vectors and values. We've sort of loosely related it to people walking around in different directions, but as we'll work with this more, this becomes not just a mathematical operation, but something that helps us measure displacements, changes in speeds, changes in acceleration, force vectors that we'll get into later. So it has a huge range of applications for us throughout the year. I hope this was helpful. If you have any questions this weekend, call or text. I'll help you out, and then have those 4 problems done for Monday. All right, guys, have a good weekend. We'll see you on Monday.